And there's national data in the US that's been used, for example, stuff through insurance, cost containment stuff that the insurers keep, like in Pennsylvania. Internationally, well, I put the UK Med down as international because we actually cover all 4 nations. We have data from Northern Ireland, England, Scotland, and Wales. So in that sense, it's international. And you mentioned, quite a lot of people mentioned professional regulators as well as sources of data as well. We've also got HCPC as well as the GDC, GMC, and so on. Good. And there are also sources of research data. I don't know whether they publish quite as much as I thought they might have, but there's a long-running study that from Oxford that started looking at doctors in the 1970s. It's a UK Medical Careers Research Group. There are a number of cohorts run in the United States in health professionals, like the Nurses' Health Study. Some of them primarily focus on health, actually physical health of the professionals. And in a sense, they might have been quite a convenient sample to follow up, but they do sometimes have information on career trajectory and that kind of thing. So there's a few of those, including the Health Professionals Follow-up Study, National Study of Male and Female US Medical Graduates. There's also other ones. I think there's the Mabel. I haven't listed it here, but I think there's the Mabel study as well from Australia. And there's ones also other from outside of US, Australia, and UK, like the Swiss Medical Career Choice Study and the WITS South African longitudinal study, which looks at health professional graduates. So you might be able to get hold of other data from around the world that's collected for research rather than routine purposes. Okay, so I might quickly just go back into Mentimeter to see if I can get you to answer these questions. Oops, my screen's gone blank. But if I can stop sharing a second, then reshare Mentimeter, see if that's worth doing. Right, I'll just reshare. So there are pluses and minuses to using routine data, and just going to share that. So again, the code up there. Can people see the Mentimeter thing again?
No, not yet, Paul. I can see the code, but not
it says, oh, right. I'll try.
Not the QR.
Right. Somebody else has put stuff in already, so somebody must be looking at it. So
possibly
somebody's putting enter. So maybe.
Oh, yeah, got it.
Oh, you got it. Yeah, there might be a lag. Like I say, it doesn't always work how you want it meant to meet. So, yeah, so large sets. Yeah, so that's a good one. Yeah, they're often very large data sets. Relatively complete ones. Yep. Coverage is a good one. Yep, they're often they're often good for quantitative stuff, but they often have little or no free text, and then in the free text they have might be of dubious quality. And nowadays, of course, having lots of free text is no problem because you can set a large language model on it rather than actually do a thematic analysis on 7,000 free text entries. But yeah, there's no need. Yep. The other one, ethics requirements, good. They often, you can't just willy-nilly analyze it, but usually if it's routinely arising and fully de-identified or at least pseudo-identified, you can often get a friendly chair of ethics to say that you don't need, NHS ethics or university ethics to analyze it. So that's a good point. Yep, avoids duplication. It's true. And again, yeah, that's a good point about not additional measurement. So you're not putting additional burden on, if you like, participants, although they're not technically participants because it's usually not research. And you're repurposing, somebody's pointing out you're repurposing data anyway. And again, available now or soon, right? That is a really good point. And one of the reasons I kind of got a bit disheartened with epidemiology was, by the time you get the answer, it's, out of date. And now with moving technology, trends seem to be moving quite quicker. That's even more true than usual. So, people would spend years setting up a cohort study, follow people up. And of course, the world's moved on several times by the time they get the answer. So it's a bit like the James Webb Telescope. You're looking at galaxies as they were 100 million years ago rather than how they are now. So, yeah, there's no influence of pressure. Yeah, well, yeah, once you start experimenting on people or doing things, or even you're asking people to opt in, you start to get selection bias and things like that. So you're hoping getting a representative samples from routine data. So that's good. Good. Well, got loads. People generated loads of really good suggestions there. What kind of challenges might people find you come across with routine data? Yeah, sometimes I have to say, lack of granularity is a big one. Quite often, you almost raise more questions than you can answer, and that's where the old mixed methods. People talk a lot about mixed methods, but to be honest, there's not many really well-designed mixed method studies where you actually use quantitative data to identify questions in particular subgroups, and then use it to guide your sampling for qualitative stuff. A lot of people say, "Oh, we're doing mixed methods," but they're not working together, which is quite frustrating sometimes. So that sometimes you can compensate for the lack of granularity if you say, "Well, we found, I don't know, female surgeons were less likely to pass their part one first time or whatever." Then you might want to do some qualitative work to get behind those data and find out why that might be. Yeah, wood tree differentiation is a good one. Gaps in data. Now, gaps in the data, yeah, they do occur, and in routine data, and sometimes it's to do with data donors, if you like, just whatever reason, stop giving you data for a few years. We had that a few years ago with UK Medical School. A lot of the data from medical schools dropped off for a while. We've got some gaps with Royal College data, so that's a good one. Again, doesn't match the research question is a big one. So when we review applications for UK Med, we have to check that the research we have the data in UK Med that actually can address the research question, because people sometimes aren't quite familiar with the data we hold. Yeah, it can be a bit superficial. I think the other thing is superficiality is one thing. I think sometimes it's very broad brushstrokes. So a lot of models we use obviously are population average models. So they can be, they might not apply to certain subgroups, your findings. Yeah, and they may not be able to answer the question. That's quite correct. Yeah, so they're not correct. They're not collected for the purpose of research, are they? So in a sense, you have to you've got what you've got, and then you sometimes have to tailor your research question according to what data you have. Good, very sensible things, and that's the end of I can breathe easy now, because that's the end of my Mentimeter thing. Never work with animals, children, or software. That's what I say in presentations. So I'll go back to my presentation to reshare. Right. Sorry about all the moving between screens. So. Right, can you see my slides again? Okay.
Yes, we can, Paul.
Yep, good. Yes, like I said, I've lost visual content now. I'm relying on audio. You can be the voice of the group, Nicola.
Thank you.
So you can shout out here at this point. Let's go low tech. Just shout out, what do people consider big data? What sort of numbers do people consider big data? Because people talk about big data a lot, but I'm never quite sure what people mean by that. Shout out a number. Anybody shout out a number between 0 and infinity.
In the thousands is the first thing that comes to my mind.
So people, could be thousands. Yeah. Any higher or lower?
500.
Yeah, 500 could be the cutoff. Yeah. Yeah. Well, I don't think there's this really hard rule. I would say the key thing is I would say it's not necessarily down to the number of observations always, because people think of the observations. So observations are the rows in your table, right? So they could be the number of doctors you've got, a number of IRCPs. I think I would sort of define it as it's kind of the point, like if you've done, I don't know, when you've done your PhD or NASA, whatever, right? And you collected data on, maybe you collected data on 50 people, 100 people, maybe even a couple of hundred people, right? I mean, I think I ended up with data about 1,000 people as part of my MD. But anyway, quite often you were dealing with stuff where you didn't need automation. You could actually look at it, you could put it in a spreadsheet, you could run your stuff on Stata, or for many people, use SPSS. Although I don't recommend it. I don't condone the use of SPS in myself or others. But anyway, people use it, so that you can manage it manually, right? So it could be, and usually you find if you've got up to usually a couple of hundred, 200 or 300 observations, usually you can manage those things manually without having to code and automate stuff. I think once you get beyond that, and it could be that you have a very wide data set with lots of variables, it doesn't have to be long. Automation is required, because otherwise you'd spend weeks and weeks going through looking for typos in it or looking for misentered things. So I would say probably a few hundred beyond is probably big data, in the sense that at that point you can't really get away with doing everything manual, or if you did, it would be a really bad use of your time. And that comes to the second point. So I would just say working with big data is more challenging than small data, basically because you cannot rely on working with it manually and picking up out of range values or correcting it or manipulating it manually, because there's just too much of it, and it would just take you weeks and weeks or months or years. So any other disadvantages? People shout out, it's a small enough group, shout out what other disadvantages might there be when you're working with big data compared to small data, and that could be like 100 or 200 observations max.
I guess you might, with small data, you might just eyeball it and spot some problem, whereas maybe with the big data, you might not spot issues as easily.
Totally, yeah. You can really, unless you run rigorous checks, you can easily miss out of range values or things that don't make sense, or things that work your way through until you're about to submit your paper and realize, some of the data don't make sense, which is not a place you want to be. So yeah, that's absolutely right. Yeah, it's much harder to spot errors and stuff. Any other issues?
You need skills in the automation and coding, and what it's kind of we may be taught the skills at medical school. For those of us that are medics, we may be taught some basic skills in small data stats type stuff, but maybe not have the skills in big data handling.
Yeah, I think that's absolutely spot on. I mean, I did an integrated degree in medical school, and I did some stats as part of that. It was a pharmacological integrated degree, but I was working with fairly small data. I didn't have to automate it. I didn't have to do any coding. So yeah, that's right. You're not, and it also data manipulation is a different skill set to stats. So knowing whether you do an ANOVA or a t-test is different to actually reshaping data, which is quite difficult sometimes, which I'll talk about in a bit. So that's right. I would say the other issue, once you get to big data, and sometimes I've ended up with like 1 million prescriptions and things I've been looking at. Once you get to really big data, depending what server or what, you're not usually working with servers or locally, things can really slow down. It's really frustrating. Your compute goes up. So you find that actually manipulating, working with very large data sets, unless you've got really good hardware, things really slow down, and that's a real pain as well. So to summarize, doing things by hand is no longer feasible. You need to start coding. It's hard to spot errors. And also the other thing is, people want big data, but with big data, I always say, comes big noise. So if you've got systematic errors in your data, that's going to be amplified actually. So I know people going on, oh, we want big data, but you know what? Sometimes you're better off with small, high quality data. And sometimes when people have applied to the UK Med for us, we've said, actually, this question probably would be best answered using a good local data set. That's, where it's come from, it's clean, rather than like our big, bigger messy one, right? So sometimes you're better off with a smaller, cleaner data set than 10,000 observations where there's missingness or there's errors. So so it can amplify us. So some key modern advances, I would say, in the world of epidemiology, and in particular observational data analysis, because remember, you can actually reanalyze trial data. Not that many really big trials in medical education, I should say, and the effect sizes of educational interventions tend to be quite small anyway. But I mean, I've reanalyzed trial data from in my mental health research, but not in clinical education. But yeah, so most of what you're dealing with is observational data. So some big advances that I haven't always seen applied often or ever to clinical education research: complex survey design. I'll be mentioning causal inference, machine learning, and I'll talk about machine learning for prediction. Maybe mention it again if nobody's heard of it last year. I probably will skip those slides because you probably don't need to know at this point, but you can go and find out about it. And you can use machine learning for causal inference, which is something we've been doing in our mental health research. Bit about talking before about data manipulation, data carpentry. That's really important. Understanding how relational databases work. That's been a really big. That's a really important thing if you're going to start working with big data. You don't have to know much about RDBs, relational databases, but you need to know a little bit how data work. Oh, so complex survey design. It's very brief. And again, this comes up a lot in papers when you review them, or people put in funding grants and funding applications. Is all right. It sounds like a really obvious thing. You need to know what your sampling frame is, right? So, and I mean, even like when the GMC come to you and say, oh, we've got 7,000 responses from our doctors, and I'll say, well, how many did you target? And often the answer is like 26,000 or something. So they think they've got an answer and strong inference because they got 7,000 responses. But you need to be clear what your sampling frame is. Who was targeted for the questionnaire or whatever it is you're doing. So that needs to be clear. And that's not always clear in research. You can, in complex surveys now, you can do cluster sampling. So you might clustering by deanery, for example, and you might say want to oversample from certain deaneries if they're under research, or say they have particular characteristics, like the demographics might be different, so you might want to oversample them. So you have to think about sampling across clusters. And stratification. So stratified sampling might be, say, if you're very interested in international medical graduates, you might want to oversample that group, particularly in a deanery or a specialty where they're underrepresented. Clearly, they're overrepresented in some medical specialties and underrepresented in others. And again, this is something we've done in the past when we did some work for, I think it was HCPC or something. Anyway, so you want to stratify your sampling so that you get enough of the people that you're interested in to compare them. And that can decrease bias and increase information, particularly in underrepresented groups. But remember, you really have to then put survey weights in when analysing. So survey weights are basically the probability that this person was sampled. They're quite easy to calculate. Large surveys like MCS, I think it was health, things like the Health Survey for England, things like that. They often have in the data you ask for, they'll have survey weights in there that you can put into your software, and will readjust the results for the fact that this person is more likely or less likely to be sampled, basically. And so you need to remember that when you're analyzing it in order to not exaggerate bias rather than dealing with it. So yeah, complex survey design, it's been around a long time. Big American surveys like N. Haynes and stuff, really good at designing complex surveys, because the idea with complex surveys is you maximize the amount of information for every dollar you spend, basically. So that's why you use clustering sampling stuff. We're not so good at it in the UK, but a lot of our big surveys will use it. The Office of National Statistics, people like that are quite good at designing complex surveys. Not used a lot in health education, I should say, but it's something we should think about with our surveys. Okay, so causal inference, massive issue. So the best way of finding out about the world is to do an experiment. And we were taught, even at school in science classes, we were told, is this a fair test if you put, I don't know, put some snails on this leaf or some snails on a dark leaf, which ones move the fastest, whatever. We're constantly, told, do an experiment to find out about the world. And it's true in most cases, it is the best way to find out about the world. But what are the issues with doing trials? And again, this is a rhetorical question. I'll answer this for the sake of speed. It's not always practical, is it? It's not always practical to randomize people to, for example, if you've got a certain educational policy, it's not really fair to sort of give some people interviews for higher specialist training and some people not, for example. That wouldn't be practical or fair, would it? And it's not always ethical either. So you can't always do a trial for everything, despite the NHR, being very trial orientated. And the other issue with trials we're becoming increasingly aware of is the findings don't always generalize well. So Richard Grieve from London School of Tropical Medicine and Hygiene has written quite a bit about this, where, well, first of all, there's the obvious thing. There's always this tension between internal and external validity. So you might have very strict inclusion-exclusion criteria, which means your trial or your study has a good internal validity, so you're very sure the results are how they are, right? But then, of course, the real world doesn't look like that. And we get this a lot in psychiatry. So you've excluded all these young people from a particular trial because of comorbidity, but in fact, that's not what your general population of child and mental health patients look like. So it just doesn't apply. So that's an issue. The other one is, which Richard Greaves talks about, resentful demoralization. It's a great phrase. I love it. And it basically means you're grumpy because you were randomized to the treatment you didn't want. So this has been raised most recently in the hormone trial for the gender dysphoria trial that they're planning, led by Emily Simonoff from KCL, who's a child psychiatrist and professor. And one of the arguments there about why why the results may not be valid from a large trial is that, if you've got these children who are hoping to be randomized to the puberty blocking drugs, and they find out they're not on that arm, which of course it'll be obvious because it's obviously can't be blinded, they're going to be so upset that actually the results are not going to be generalizable. So resentful demoralization, but that was shown actually even years ago in a diabetes trial, and because David Cameron's saying, oh yes, everyone should be doing this in diabetes, and it turned out that the resentful demoralization had played a part in the results they weren't mimicked in the real world. So cause inference. So in RCT, RCT's randomized control trials, randomization is what we call, technically, it's what we call an instrument. So an instrument is a way of getting, an instrument is, and I'll mention this later, is a variable that is related to the outcome, but only by its relationship with the condition or the exposure. So randomization is an instrument because randomization is associated about which arm of the trial you go in, but it shouldn't be related to the outcome. And that's the definition of an instrument. So, so you have you have your population there, you randomize them to a control group and an intervention group. And you hope that on average, people look the same in both groups. And Don Rubin realized that if you could make observational data look a bit like it was a result of a randomized trial, you could establish causation. It was kind of an interesting and important insight. So, and now getting to causation is really, really hard in observational data. And it's very hard because it's based on at least 4, depending how you count them, 4 or 5 strong assumptions. But I would argue that even if you cannot establish causality, the approach is always better than using a standard stats approach, because you at least get closer to causality, even if you never quite get there. So the best way of starting off with that is to design what we call a directed acyclic graph or a path model with experts. And those could be experts, they could be educationists, they could be patients, they could be a range of experts, people with relevant lived experience. And there's a methodology that was published a couple of years ago by one of my colleagues, how to do that. So this is an example. This is a co-produced graph of path diagram. It's not technically a directed acyclic graph because there's arrows that go up as well as down. So it is a path model. So here, this is how we speculated. PCR here stands for posterior capsular rupture. So that's someone popping your eyeball during a cataract operation, which is not a good outcome, I should point out. And so we were speculating, how does performance in the Part 2 practical exams of ophthalmology that ophthalmologists take during training, how could it relate to patient safety? So we got, various people, got an ex-president of the Royal College of Ophthalmologists, the chief examiner, blah, 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 and people involved in, practicing ophthalmology as well as trainees, to get together to sort of say, well, does this look like how you think these different parts of education of ophthalmologists and the exams relate to each other causally and ultimately result in, or not, might relate to patient safety during cataract operations. And we derived this, and we were able to test it. And I have tested it. The paper is currently under review, I should point out, but we did put numbers on this. We populated this with data. We'd linked cataract data to the UK Med, And we populated, and there's numbers on all these paths, which I'm not at liberty to share with you, only to say it's a very, very interesting story, and probably, to our knowledge, the first time people have linked performance in practical, not written, but practical clinical exams to patient outcomes. So that's what we do. We don't sort of start off just throwing everything into a multivariable model. We actually think about how are these variables causally related to each other, do we think? And if we're wrong, it doesn't matter, because the data, if it doesn't survive first contact with the data, we can go back and revise those models. But it's a better place to start than just shoving all your data into a multivariable model and seeing what hangs in there. And in general, getting together and putting up a path model together, creating a path model with experts, is always going to be better than doing the slavish thing, which is you start off with a univariable model. You just like see how everything relates to everything else, you know, one at a time, if you like. And you bypass, you actually bypass the multivariable model. By that I mean just shoving everything into a multivariable regression equation and just seeing, you know, what hangs in there. Because one of the issues that's been highlighted by shoving everything into, say, multi-level model, is you risk something called the table 2 fallacy, which is not that widely known outside of epidemiological circles. And it's basically what's happening is it's that actually when you put everything into a multivariable model, you're assuming all those things are confounders, but actually that might not be the case. And therefore your results may be spurious. And you also might, if you use stepwise regression as well, you might exclude certain variables that are still important. So that is why it's seen as poor practice now. And if you must do a flat variable regression, then again, I'm not going to go into it because I've probably pitched this to a bit high. But again, people are using lasso, which is a machine learning technique, to select variables that go into, you know, that are independently predictive rather than the traditional stepwise regression. And also, again, when we're giving feedback to people who are applying to the UK Med for data, they're often saying, oh, we'll put everything in, we'll put gender in, we'll put this and that in. And that's, well, my answer is often, and again, when I'm reviewing papers, is, well, fine, if gender is relevant to your policy, put it in. But if it's not, why are you putting in to your model? Because you should really be putting stuff that are policy, things that are policy relevant into your model, not everything that's available, like that in the kitchen sink. Because, you know, people are adjusting for things, but why you're adjusting for it if that's not relevant to your educational or health or regulatory policy, say. So, and one of the reasons causal inference is very difficult from observational data is it's based on strong assumptions. And there's different ways these are presented. This is the way I present them. And I have to warn you, there is a warning here. People who got into the causal inference have created a very impenetrable language around it. But I did my training, I think in 2017 at the London School of Tropical Medicine and Hygiene. I did their causal inference course, intense week of that. And it takes a long time to understand what things mean, because they like many experts, they use language to you know, make it more, perhaps sometimes more complicated than it is. So there's 4 assumptions. One of them is positivity. They call positivity, right? So positivity, again, it's not an intuitive thing. It just means you've got a non-zero chance of every combination of variables being seen. There's no empty cells. So if you want to control for, say, I don't know, gender and ethnicity, right? If there's no one of a certain ethnicity who's female, the positivity assumption is violated, so you can't recontrol for it, right? So that's all it means, is that every combination has to have at least, you know, some observations. That's kind of what it boils down to. And again, there's this term, rather arcane term, SUTVA, which is stable unit treatment value assumption, but that just means everybody's chance of, say, an exposure and outcome is not influenced by everyone else. So an intuitive example for that might be, I mean, the one that's often given is if you do a smoking cessation intervention, right? Somebody that sees one of their friends stop smoking, even if they're in the other control group, might be more likely to give up smoking. So it's not independent, is it? And again, an educational example might be if you do an educational intervention, like additional revision for somebody or whatever for certain groups. Well, their mates might benefit indirectly from that because they might start sharing things they've learned, right? So at that point, the set for assumption is violated. But anyway, I don't know why they use that term, but there you go. Exchangeability, again, I think they would probably, it's sometimes called ignorability, but actually what they really mean is no unmeasured confounding. So it just means that every person could be exchanged for everyone else once you've controlled for all the variables. And so I don't know why they use the term exchangeability. I do know technically why they use it, but I think it'd be much better if it's just termed no unmeasured confounding, because that I would say is no unmeasured confounding is probably the assumption that's violated most often in causal inference. Consistency, all that means is everybody got a comparable exposure or intervention. So if you give people, say, extra tuition to pass their CASC exam or whatever, if they're doing a psychiatric membership exams, right? If you gave some people, say it varied in length, so one person's workshop training session lasted 90 minutes, another person only got half an hour, the consistency assumption would be violated, basically, because it's not really the same thing. So they are the 4 pillars of causal inference, effectively. And I did find an interesting paper from Iran, as it happens, which summarized this very nicely and got, using the power of Notebook LM via Gemini, got to produce some of the slides. I haven't used them all, I just used some of them. So I must declare this was generated from a paper. So effectively, it's just saying you've got an exposure, you've got an outcome. The exposure in clinical education could be a selection thing, it could be a selection measure, it could be an education intervention. But that relationship between the exposure, if you like, and the outcome is muddied by potential confounders. So these are some slides I put together just to try and illustrate some of these concepts. So a confounder is basically just a variable, to recap, but most of you have probably been taught this at medical school anyway. So you've got an exposure, X1, you've got an outcome, Y, and you've got this confounder sitting there. So a call confounder is just something that is both associated with both the exposure or intervention and the outcome. That's all it is. It's something that sits there and it's exposed to both. So, for example, it could be, I don't know, I'm trying to think of an educational example, common one. So, for example, if you do work on fitness practice or disciplinary stuff, right, male sex is associated, it's certainly associated with the risk of disciplinary, but it might be also associated with another potential risk factor, such as, I don't know, previous convictions for driving offences or something before medical school. So yeah, so you can see how a confounder could confound, if you like, the relationship between the exposure and the outcome. Now, people less commonly known is this idea of reverse confounder, which Greenland came up with in the early 2000s. And it's a special case of Simpson's paradox. For those who remember Simpson's paradox, if you don't, you can always look it up. So reverse confounder, as the name suggests, it actually amplifies the effect between X1 and Y. So best example I can think of off the top of my head is in US competitive colleges, top colleges in the US, there is an inverse relationship between sporting prowess, athleticism, and SAT score, or SAT score, your grade point average. And that is not observed in the general population. So, and it's because you either get into a top college because you're a school football star, American football star, I should say, or because you have high SATs. So in that case, entry to college is acting as a reverse confounder and producing a sort of correlation, albeit an inverse one. Sometimes it's called a collider, that where there wouldn't normally be one. Okay, but there's examples in medicine as well of that. So, for example, diabetes and kidney disease, well, not diabetes and kidney, because diabetes is linked to kidney disease, but sometimes co-occurring kidney disease with other things is more seen as hospital populations because it was bad enough to be in hospital. Anyway, so it basically produces associations or reverse associations where you wouldn't normally see them. So you need to be aware of reverse confounders because you'll miss them if you just put stuff into stepwise regressions. And there you go, it's got a positive effect. Again, different to a confounder is a mediator. So a mediator is this time between the exposure and the outcome, the part of the relationship between the exposure and the outcome is mediated by this variable. So the arrows are pointed the other way now. So it's not a confounder, it's actually mediated. We've done some modeling of things that may be mediated. We've looked at things like language, fluency in overseas doctors and performance and stuff in clinical exams. So yeah, so we've got plenty of examples of things that are mediated. And again, you don't want to put those into multivariable regression either if they're not confounders, because it'll make your results go funny. And lastly, you talk about instrumental variables. I've not seen examples of this in educational research, but there are probably some out there. Instrumental variables are kind of the holy grail of causal inference. So you've got an instrumental variable and it's related to the outcome. Well, the instrumental variable here is I1, and it is related to the outcome, but only by its relationship with the exposure. So I'm sitting here in York as we speak, which of course was the childhood home of John Snow. So John Snow famously removed the handle of the pump in London that was the source, allegedly the source, the real story is more complicated, of the cholera outbreak. So it turned out there was two water companies in that area of London at the time, and one of them was producing water that was contaminated with cholera, the other one wasn't. So that was a good example of an instrumental variable. Water company A, the water companies don't cause cholera, but it was related to cholera by the fact it was mediated by the exposure to the water. So that is an example of an instrumental variable. And I've got an educational example later on as well I can mention. So just to give an example, so this is something I published quite a few years ago with Work Psychology Group. So we were looking at overseas doctors and their performance in clinical skills assessment of the GP exam. And here you'll see we put together a path diagram which we tested with the data, quite a large data set, and looked at how, because we know that English fluency, for example, influences your situational judgment test score, which in turns influences how well you do in clinical skills-based exams or anything that involves interpersonal stuff. So here SJT score is a mediator between English fluency and clinical skills score in trainee GPs, right? As is your clinical problem-solving score, your CPST. Again, that's a mediator. And here you'll notice they're all square boxes because they're observed, except for English fluency. So here I modeled English fluency as a latent variable because we can't observe English fluency in this context directly, only by the results of the IELTS, which has 4 subtests: reading, speaking, writing, and listening. So I used those as ordered categorical indicators of a latent variable. And the advantage of working with latent variables, without going into it, is you're working directly with the latent variable and therefore the errors incorporated. So it's actually much better than actually, say, summing all the scores or just looking at overall IELTS scores. It's a much more elegant and informative way of looking at it. So that is a good alternative to just plopping everything in a multivariable regression. So standard approach is not really fit for causal questioning. You just end up looking at average effects. And I'm not going to dwell on this because you're due a break, or maybe slightly overdue one, only to say there are different methods of getting to causality observational data. Most common methods are inverse probability weighting, G formula, and something I've used in my mental health work, which is called targeted maximum likelihood estimation, or TMLE. We tend to call it targeted learning now, and that's based on machine learning. And effectively, it works. The principle is for propensity scores is again going back. You want to make your population look like they've been the result of a randomization process. So the propensity score is you're trying to weight stuff given the probability of the exposure or the intervention. So you actually weight everyone's observations according to that. G formula is the opposite. You're looking at the probability of having an outcome. So inverse probability weighting is a model, if you like, for the exposure. G formula is about a model for the outcome. So they're modeling different aspects of the process, but TMLE, which I tend to use, I tend to favor it, partly because I'm into machine learning. That works both ways. It both produces a model for the exposure probability and the particular outcome, both at the same time. So that's what we call it doubly robust. So even if you get one model wrong, you still get an unbiased, a correct result. So that's one of the reasons we tend to favor TMLE. But I'm not going to go into it because it's a bit technical. Only to say that there are methods you can use to get towards causal inference from observational data. Often that involve creating models for either the exposure or the outcome, or both at the same time using targeted learning. And I'm not going to mention that because that's more machine learning. But we basically use machine learning to create those models. So just to finish off before a quick break, instrumental variables, as I said, it's an instrumental variable I1 is not related to the outcome except by the exposure. I always say a bit like unicorns, you know, they're hard to find. They're lovely if you do find a unicorn, and a bit of a cheat code for causality. So they must be strongly related to the exposure, although you can get away with more weakly related ones. I mentioned John Snow's cholera example, which is a nice one. Other nice intuitive example is state tobacco taxes. So for example, if you're in the US, some states have higher tobacco taxes than others, and strangely enough, the states with the low tobacco taxes have higher rates of lung cancer. But taxes, much that we don't like them, don't tend to cause lung cancer, but they are a marker of, obviously, tobacco usage. So they are related to lung cancer through tobacco usage. So in that case, the taxes are an instrumental variable. So I was trying to think of an example for clinical education. So for example, one question might be, does building a new medical school reduce mortality in a population? You know, the more doctors you have, does that actually improve longevity in your local population? It's a really interesting question, isn't it? So you build your new medical school and you hope then it produces more doctors and you hope that results in reduced population mortality. And I guess Daniel Pearl was his son who sadly got murdered by jihadists. But Judea Pearl talks about closing backdoors. So often with these things, there can be a backdoor. And here the backdoor is, what if population mortality lowered because medical school is like an anchor institution, it increases employment, and therefore you've got increased economic prosperity and it reduces. That's one question. So you have to find a way of shutting that back door. But in this case, the new medical school, if you like, could be seen as an instrumental variable, and answering the question whether more doctors reduces population mortality. Right. I'm going to stop sharing there because you are due a 5-minute break for comfort and to get some coffee or whatever, and in line with educational theory that everybody's attention span should be well and truly exhausted now, unless you're a Zoomer, in which case it was probably exhausted within the first 35 seconds. So anyway, any questions about that before I give you a 5-minute break?
Paul, I was curious to know, you mentioned the different levels of data and you classified the UK Med as international.
Yeah. Well, it depends if you're Scottish or Welsh, you probably do this because, you know, they see themselves as a different nation. English, I'm not sure. English may not see it as international.
So it's international as in the 4 nations rather than broader than that. Yeah, okay, got you.
But now, interesting though, I think, I'm trying to remember whether we have, I don't think we've got data from places like NewMed or our Cyprus Medical School at St. George's, because I don't think we do. I think we had this discussion years ago, because theoretically we could have got data from like our Cyprus St. George's campus or say Newcastle's NewMed, but we don't, I don't think. But it is international in the fact that we have different jurisdictions, of course.
Yeah, brilliant. Thank you. Can't see anyone else asking questions. So yeah, should we break for 5 minutes?
Yep, if people can be back at 15:37, that'd be great.
Brilliant.
Oh, well, I hope I didn't bludgeon people into submission too much. with my causal inference stuff.
What's left to cover, or what's your plan for the remain? Because we've got half an hour now.
Right. I tell you what I'm going to do, given we've got half an hour, is I'm wondering whether I should skip the bit of machine learning, given that people aren't at a very high level in terms of stocks knowledge. So I think the thing I might find most useful is I'm going to say a bit about, you know what I'm going to do? I'm going to say a bit about use of AI in observational data research, just a couple of slides. Then I'm going to say about particular issues in med-ed research, summarize, then I'll give a quick example on UK Med, and that should be finished by 4. Does that sound okay?
Yeah, you might want to leave a bit of time for questions.
Oh yeah, I will do.
Other than that.
Yeah, unless I leave them stunned, unless I stun them into silence.
Yeah.
Yeah, so I'll do that. As usual, I have been over-inclusive anyway, but it's always better. It's like a haircut. It's always easier to take it off than put it back on.
Yeah, absolutely, absolutely. And you don't know what level people are at, do you?
No, well, I wrote these, and then I got the biographies, and I'm thinking, most of these people are not quantitative, so.
Yeah, yeah. And we've also got a mix of professions as well. So we've got medical and kind of, there's lots of kind of nurses, NMAPs and chiropractors, etc. So there's a variety of professions as well. Yeah, that all sounds good. And it's really good timing for me. We've got our UK Med work package starting next week on our IMG study. So yeah, it's been good for me to start to think about it, because it's not really my area of expertise at all.
Who's doing the hands-on work with the UK Med?
We have recruited a guy called Paul Collings. So he's starting in the medical school, and he's an epidemiologist by background. Hasn't worked with UK Med before, but seems to have lots of great skills.
Good.
Yeah, and so Tom Gale and Kath Wolf are kind of leading that work package.
Oh, well, Tom's done lots. I think Tom's done quite a bit of work with UK Med.
Yeah, he has. Yeah, yeah.
And I noticed Plymouth had got £11 million for a mental health research group. It was announced yesterday.
Yes.
So
yeah.
I should point out, I'm the York PI for the Bradford bid, which we went in for the original ones and were told to go away and given the booby prize of £2.5 million.
Right.
And then told to resubmit for the mental health group award, but we were told not to submit for the last one that Plymouth got awarded.
Yeah.
We were told to hold off until we got ahead of steam and then apply, like probably towards the end of this year or next year. But the thing I'm twitchy about is, given the financial climate, will they actually have another call? So we'll see.
Yeah. Rebecca Hardwick led that, and Richard Bing. I think similar to you, they weren't successful first time round. They had to put in again.
Well, I'm thinking now. I'm thinking maybe we should have put in that round as well, because, like I say, the trouble is, especially like if they suddenly decide to put everything into tanks and guns, because this happened with the Global Mental Health Fund, that we had millions and millions of pounds for global mental health, and now they said no, it's all being put into defence. So yeah, so who knows what's going to happen? So yeah, we might have been better off having a go at it last time.
At least you got the booby prize, though.
Yeah, well, £2.5 million is a pretty good booby prize.
It is. It's fantastic.
But like I say, I mean, to be honest, yeah, I think they liked the project. I think it was mostly, I think they wanted to see more kind of capacity building in Bradford, and that's why they gave us the Mental Health Leadership Award, which is fair enough. So anyway, but I noticed Plymouth was listed on the successful ones yesterday. Good. Well, it's gone to 15:37. I should get ready to start if people have come back. Okay. So I thought to myself, hold on, why has it gone there? I'll just zoom through these. Hold on. I'll just start resharing. My slides are going funny. I think, has everyone gone? It's a bit of an awkward step. I'll just reshare. Okay. Just try to put it to full screen again. Right, can everyone see? Oh, it should be appearing in a second. Can everyone see my alert dangerous, right? Use of AI. I thought it was worth mentioning AI because it's very topical and people increasingly relying on ChatGPT and other things to do data analysis or to tell them how to do data analysis. So I thought it was very timely that I mentioned this. So they are very large language models, such as ChatGPT, Gemini 3.0, et cetera, are powerful tools, and they can provide very good statistical advice. Actually, better. They used to be when ChatGPT first came out in 2022. It was pretty ropey, but actually they have got a lot better. And Gemini 3.0, which we have access to at the University of York, has been quite impressive when you ask it the right questions. And AI coding systems are very rapidly advancing, but effective prompting requires good foundation understanding. So I find unless people really understand what is it they're asking and why, they're often either getting bad advice from the LLM because or they're misapplying code or they're producing code that isn't really doing what needs to be done. So it's no substitute for having a good foundational understanding of statistics and data management and stuff. And it's very easy to misapply code or incorrect if you don't understand principles. But if you do have a good foundational knowledge, they can potentially speed things up loads. But I would also say hallucinations are more of a challenge, I think, than the tech companies realized they would be. And the hallucination rates are still around 5 to 20%. Some of the newer models claim it's down to 5%. But honestly, I mean, even last week I got some some amazing references offered when I was querying something, but then when I checked them out, they were completely made up. Plausible, but completely made up. So you have to be quite careful. So I think once people understand something about stats and stuff, I think that they're very powerful tools, but really shouldn't be used without a good understanding of what it is you're trying to achieve, I would say. I had to put this in the last minute because this blew my mind, basically. I was very frustrated last week with there's this software we've got a free trial of for speeding up systematic reviews. And I know this is about systematic reviews. It's not about thing, but I have to tell you. And so in under an hour, I produced my own software package to do abstract and title screening and have the functionality I wanted, which included getting a relevance score for every paper, which the software didn't, which I should point out is $50 a month, this software. And I did this completely free. You do need an API key. I just used a free one for Llama 3. And the reason I'm telling you, it completely blew my mind that this 25 minutes of it was debugging the API, the application program interface linked to Llama, but it came up with this in under an hour. I absolutely couldn't believe it. So I only mention this to show the power of vibe coding, if you like, or AI. So if you're, for me, it just raises lots of questions about statistical software, even like, can you actually produce a statistical software package in half an hour using, this was done in anti-gravity, which has just been released by Google. So if you have a particular, say you want to do particular data visualizations or something, you can literally produce your own software package without any coding in under an hour. That will do this. So honestly, I felt like Dr. Frankenstein when the so-called monster came alive, because I was both amazed, delighted, and horrified, because I was still thinking hundreds of thousands of people in the software industry are going to lose their jobs over this, because this just blows software as a service out the water. Anyway, I just mentioned that because I've been astonished at how quickly AI has developed, and you could use it for things like data visualization or even bespoke statistical software creation if you want to. Anyway, I digress. Okay, so one of the key challenges with clinical education, when you're doing workforce research, selection occurs at different stages. So people get selected into medical school, don't they? People get selected into postgraduate training, and people get selected by regulation. So people like, for example, overseas graduates get selected in via the PLAB and various things. So selection effects are at work, and this changes things. So Chris McManus wrote a great paper in 2013, which illustrates this really nicely, about construct level predictability. So one of the other issues is trends are changing in policy, so it gets out of date. So the issue with selection is if you're selecting a population, it actually attenuates the correlation between the prediction and the outcome. So, for example, somebody announced many decades ago, A-levels, that's obviously grades in England, A-levels are no predictor of performance in medical school because there's virtually no correlation. Well, of course there's virtually no correlation because you've selected everyone at the time. Everyone had to get, whatever it was, 3 Bs in those days, but it's higher now to get into medical school. So there's hardly any variance. Of course, there was hardly any correlation. So people can come to spurious conclusions because of these selection effects and the fact that you can't observe the outcome in most people who were tested. So most people, about 40% of people who apply to medical school get at least one place, get a place offered every year. But obviously that leaves 60% who don't have an outcome in medical school. And so there's also this issue about right censorship. So for example, in A levels, you can't get more than 3 A stars on a tariff. So that comes into play. So this is a big issue in a lot of the work we do in clinical education because selection works at different ways. So for example, in some of our work in UCAT, or formerly known as the UKCAT, you've got all these unsuccessful applicants. So you can't actually observe the outcomes in them because they never got into medical school, did they? So so Chris has got this nice diagram he used in his 2013 paper, and it shows, without going into too much detail, the green line, the very shallow slope, is what's observed. That's what you observe in the selected data. But actually the true correlation between the outcome and the construct you're interested in is the blue slope, which is a lot steeper, isn't it? Has a bigger effect if you correct for that. And again, some of my work with UCAT, we run into this with some of the older A-level data before A stars were invented in 2010. You can't observe people's performance beyond 3 A stars. So that again reduces the effect size you see in some of these studies, and you can conclude that it's a very weak effect size wrongly. So there's lots of ways you can adjust for this. So I've used Tobit regression before, which accommodates that. There's various formula that the psychometrician Thorndike came up with in like 1950s and stuff. I still prefer multiple imputation now. So in multiple imputation, say, go back to our situation where we can't see the outcome. In our unsuccessful applicants, look, they're sad, they didn't get a place at medical school. But what we can do is we can simulate them using imputation. So that's where we actually use the observed data to put in plausible values for things. This is the grade at medical school you would have got had you got in. And we actually do that usually, well, I put it here about 5 times. That's 5 imputed data sets. But actually, I would usually use at least 20 or 30. So we have 20 or 30 values, and we can then analyze all those data and smush them all together to get an average effect. That's what we do, and to get an idea of actually what the true relationship between, let's say, the test assessment is, the selection assessment score, and the outcome of interest. It gives you a much more realistic idea about that. Otherwise, you might not see any correlation. Okay, I'm going to talk a bit about data carpentry, which is the data manipulation we mentioned before. Often involves some data linkage and reshaping, really requires some basic knowledge of relational database theory, which was developed by a certain Edgar Codd in IBM in the 1970s. IBM tried to suppress his work, interestingly, because they just built a big mainframe computer and it couldn't do relational database theory. But he wrote his paper, and Larry Ellison, a certain young Larry Ellison read it and started a little known company called Oracle, and became, at one point a few months ago, he was the richest man in the world. So it just goes to show sometimes it's worth being an early adopter. So, but basically, one of the difficulties you get in clinical education data is you get repeated measures. And so, for example, that will sometimes involve having to reshape your data, right? Because you've got, for example, repeated ARCPs, annual review of competence progression. So, you might, each row might be a doctor, but each doctor might have 6, 7 plus ARCPs. So how do you actually rearrange those in a way that you can analyze the data? How do you make sense of that? And that often involves some data reshaping. So I won't go on about Edgar Codd's normal forms, only to say that, it was really about trying to get your data into a shape that makes sense, where anomalies and errors aren't going to creep in, and that's most parsimonious as possible. Anyway, so the idea is you get all these tables, and I'll show you the UK Med one in a bit. But the idea is you should have a way of linking all these different data tables uniquely so that people don't get in a muddle, and that you can end up drawing out the table, if you like, for analysis in a way that kind of makes sense and doesn't have redundancy or errors in it. So this is what it looks like for UK Med. So clearly we've got lots of data from different data donors. we've got all the GMC data, we've got UCAT data from selection and so on. But of course, there's no one way you can put that into one big mega table without having lots of redundancy. So effectively, what you have to do is you have to join up all these tables in a way to produce an analytic data set, which you then even may have to split up or reshape. So, and that can be a non-trivial task. I remember years ago, a university had applied for UK Med data, complained bitterly that the Health Informatics Centre wasn't reshaping their data for them. And that was a very unfair complaint, because actually reshaping data often involves a lot of decisions, such as should we take people's first attempt at an exam or last attempt at an exam? It wasn't something that the Health Informatics Centre, as a data repository, it wasn't their job to do that, because it involved some subject knowledge about medical education. So you need those skills, because nobody's going to do it for you effectively. So for example, this is a very common situation. You have wide data, you've got, say, this is something I come across a lot. So you've got your doctors, each doctor has its own his or her own individual ID. And you've got a load of ARCP. Say you take everyone's first 4 ARCP outcomes. Okay, so each one of those rows is individually identified at this point in wide format by the doctor ID. But if you're doing multi-level modeling and you have to look at IRCPs within doctors, you need it in long format. So at that point, each row won't be individually identified by the doctor's ID. So for that reason, you'll need to create an ARCP ID as well. Otherwise, you're going to get in a right pickle. And at that point, usually most software, reasonable statistical software, will carry out multi-level modeling, whatever, which will accommodate for ARCP outcomes clustered within doctors or whatever it is you want to do. But that, that is quite, it can be, if you've got a large, messy data set, that can be quite a difficult, challenging task to do. Okay, so just to summarize my educational epidemiology stuff before giving you a very quick 5-minute example in UK Med. Do draw path diagrams or DAGs before you do your analysis. In general, only include policy relevant variables to avoid the table 2 fallacy by not throwing everything into a multivariable model. If you do want to do variable selection, use lasso rather than stepwise methods. Also, I recommend the use of multiple implementation for missing variables, and that includes missing outcomes, because it will also address attenuation of range for personal selection methods and range restriction, although other range restriction correction methods are available. And I would say, if you're going to do any decent quantitative work, say you're proposing to do it as part of a fellowship application, you'll need to put a programmed plan together in that fellowship proposal to develop your stats knowledge, as well as software and data management skills. So stats knowledge is one thing, and it overlaps, but is distinct from having then the skills to actually implement it in software, and also to manage your data, which is again a separate set of skills. And don't throw everything to multivariable regression models, or use stepwise regression. And also don't use list-wise deletion for non-trivial mixing. So if you've got, like, say somebody's got 30% missing on a variable, don't delete all 30 observations, because that's very wasteful. Just impute the missing values, I would say. Also, don't rely on A for coding or stats, although it is a helpful adjunct for those who actually know about the stats and what you want to do. And I've just got a quick case example to go through to finish with. So, all right, the question is, this is going back a while. This is during COVID, Health Education England, as it was then, suspended face-to-face processes for recruitment to specialties. And their question was, is it worth putting them back in? So Work Psychology Group wanted to look at this, and they sort of pulled me into it for some consultancy. So the previous evidence was, and this was some work that Chris McManus and others had done years before, showed that the actual face-to-face selection centre scores added little incremental value when predicting clinical skills assessment scores or exit exam scores for GPs. And they weren't sure if this also applied to psychiatric training. So the question was, is it worth us spending lots of money putting back a selection centre or not? If we found the GPs, it added very little value above things like the situational attachment test, which is cheap and cheerful to deliver. So that was the question they posed, and we added some data, and we tried to answer it using UK Med data. And the second question for that was, if we do put the selection centre back, who should we do it for? So anyway, I won't say too much about the UKMed because we've got a website, and I've already shown you the key. But so I'll go straight to research questions. So do choose research questions where you hope your answer will impact practice, and that's now still relevant or relevant in the future. And again, if you're going to use UKMed, don't try and pose questions that couldn't be answered by the data, although we're good at balancing those, or purely of academic interest, or could be better answered using local data. I've mentioned that. So this was the application put in P155, which applied for the data to use. And these are scoring criteria. I won't go into that. So we started with a hypothesized causal model, and our idea was your performance in the practical exam, the CASC, the Clinical Assessment of Skills and Competence in MRC Psych, was predicted partly by your performance on knowledge-based papers, partly by how you performed in the selection centre at recruitment a couple of years earlier, and also how you might have performed in the SJT at the MSRA at selection and the clinical problem-solving test. But that was mainly mediated by both the selection centre and the written paper. So we had a sort of, if you like, started off with a causal model about how we thought these things were related to each other. Anyway, I'll go into that. Anyway, we managed and cleaned the data, standardized the written exam scores, and we imputed missing values, including for the outcome where they were missing. And we looked at the univariable relationship between all the measures, or like a big correlation matrix about how those things were correlated to each other. Most of the things, I would say in the social sciences anyway, everything's at least correlated to everything else at least 0.2. But here you can see that some of the educational things were correlated reasonably moderately, with each other. So we did that. We did some work looking at the effect size for each selection measure on demographics, but that wasn't the primary question. And then we populated and tested the path models, first for all applicants. So we can see there, for all applicants, the selection centre, the path coefficient to the CASC exam from the selection centre was 0.33, which was exactly the same as it was for the situational judgment test score as part of the selection process, as part of the MSRA. So you could say there that the contribution, the predictive contribution of the selection centre performance was the same, or indistinguishable from that of the SJT. So it was doing something, and it was roughly the same as the SJT, which was different to the GP model. Actually, the GP model showed very little unique contribution of the selection centre scores, so that was different. You can see they're both the same there. And then we looked at those who'd done relatively poorly on the situational judgment test. So we hypothesized that if you've done relatively poorly on the SJT, maybe the selection centre was more important. Maybe you should reserve the selection centre for those who'd done quite poorly. And this is something they've done in the past when they HE were playing around with selection centres. They're saying, well, in some specialties, if you scored so much on the MSRA, you were excused the face-to-face selection centre process. So, and they'd have a cutoff for that. And now I developed a cutoff using screening theory, receiver-operated characteristic curves. So I won't go into that. But we found there, for those who'd scored quite poorly on the SJT, actually the selection centre independent prediction of CASC was actually more than that of the SJT score. So for those who was doing badly at the MSRA, actually the selection centre seemed to be doing more heavy lifting and was actually probably something that you might want to put in there if you wanted people to pass their exit exam. So anyway, I've already talked about the do's and don'ts of analysis, so I won't do that. So so we had a few of us involved in that, including various people involved in psychiatry, training and selection. And we did have resources to do the work, because often people apply for UKMeds, don't have the resources to carry it out, but we did. So we did end up publishing it, BJ Psych Bulletin, and we did a report from NHSE, which was obviously NHS England, which is what HE became when it was shut down. And of course, I'm not sure what NHS England, of course, is also going to be abolished soon. So I'm not quite sure where where the educational stuff will go. And then we sort of published it, and we, there's some do's and don'ts for dissemination. Now, although I have to say, HEE, as it was then, did not listen to our results. So I suppose there is a sting in the tail of this tale, which is, even if you do the good science, and you get the evidence and the answer, the policymakers don't always listen to your results. So they did not reinstitute selection centres for anybody, basically because they said it would cost too much in terms of resources and money. So that is a slight twist in the tail, but it was still worth doing. It was still a policy relevant question. So I'd say if you're applying to UKMed, general focus on research worth doing, but research that is doable. Keep focused on policy relevant questions. Make sure you have the right resources, including team, time to actually do it. And also, don't let your findings go cold and become a well-kept secret. Make sure you let people know and disseminate your findings, because we've had quite a few applications over the years. 5 or 6 years later, people still haven't published their findings, which is not a good use of resources, really. So that is all the stuff I'm going to talk about, and I shall stop sharing my screen. You've got a couple of minutes, hopefully, for questions. That's a whistle-stop tour. You probably feel like frog geese at the moment, having been force-fed.
Brilliant. Thanks, Paul. That was a comprehensive overview of big data, particularly in relation to educational epidemiology. Anyone got any questions or thoughts or comments? Richard?
Yeah, thanks a lot for the talk. It was super interesting. I struggled to keep up, but it was really good. I mean, just a bit off topic, but do you think peer review still works in this setting? Because I was just thinking, there's going to be so few people with enough knowledge to review, to review these sort of outputs, and then you've got obviously people using AI, and then people using AI to do the reviews. So it's like AI reviewing itself. And does it still work? What do you think?
Well, to paraphrase Winston Churchill, peer review is the worst possible way of assessing quality of grants and papers, apart from all the others. It doesn't, I'd say, because this is an HR ClinEd incubator, I'd say there are particular issues I've noted and mentioned over the years with clinical education, which is a shortage of qualified peer reviewers. Now, the grants, we're getting better with an HR. I think the incubator has done quite a lot to raise the consciousness of workforce and clinical education research with NHR, because one of the issues we used to run into was you'd put a really good bid together, and then somebody would look at it who just spent their whole time doing, randomized trials on kidney disease or something, right? And say, well, why aren't they doing a trial or something, right? So NHR was dominated. A lot of the peer reviewers were trialists. I think now we have more people, like I think Karen's involved, Karen Matic's involved. We've got more people involved on the funding panels who understand educational and workforce research. So I think there's less of a problem. So that's about grants. Papers, I still think it's an issue, because both ways. I think sometimes people are too scathing about papers because they think it's too complicated, they don't understand it. And I've had at least one paper rejected, which actually ended up making quite a big policy impact years ago, because they said it was too complicated for the readership to understand. I won't mention the organ, only say it was a very top educational journal. And it was reviewed twice. It went through peer review twice, and in the end they concluded it was too complicated. So that can be an issue with meded stuff. I think it's also partly, though, I've learned it's partly the job of the writer, the author, to make stuff comprehensible to readerships if they're non-specialists on stats. So I think we can do stuff as authors as well, if that answers your question, Rich.
Thanks, Paul. Asim?
Yeah, hi. Yeah, thanks. Thanks, Paul. That was really helpful. Mine's more of a signposting question than anything else. I happen to have done some clinical epidemiology research like 10 years ago, so I managed to keep up with, like, optimistic guess, like 80% of everything you were explaining. But a lot of the new things around educational epidemiology were new concepts to me. The research I'm doing is kind of relating human factors intervention to patient safety outcomes is what I'd like to do for the next part of my project. So I'm designing the intervention. But a lot of what you said about causal inference sounded really useful as a way to maybe look at outcomes once an intervention is put into place. In terms of finding out more about learning that technique in a way that someone who's never come across it before can get their head around, is there any direction I could go into to learn a bit more?
I don't think the London School of Tropical Medicine and Hygiene run their causal inference course anymore, because I was looking at it for somebody else, because that's a very good course, although it's quite expensive. But there are lots of YouTube, as a premium YouTube subscriber, I can say there are lots of good YouTube materials about understanding causal inference. I'll just see if I got it in my bookshelf. There's a book by Judea Pearl about causal inference, the Book of Why, which I've introduced it to some extent, but I guess he's coming from it at a particular angle as well. So I would say I would start almost with YouTube and some simple primer papers, because some of the books, I remember reading a book on causal inference years ago, and it was pretty turgid and mathematical. So I'd start off with like YouTube and maybe a simple primer paper.
Amazing, thank you.
Thanks, Paul. Anyone else? Any questions, thoughts? No. Okay. Brilliant. Thank you, Paul. That was absolutely fantastic. It gives me so much to think about. I've learned so much. Hopefully everyone else has found it useful too. The next session, the next masterclass is going to be at the end of March, and we have, who do we have? I've written it down here. We have Peter van der Graaf, who's going to be talking about knowledge mobilization, and Karen Matic to talk about her career journey. But thanks everyone for joining today. See you again soon.